Do you hear me now? Check it now. Do you hear me now? Thanks. All right. I got some question via Discord that it was not that clear. So let's go through again with the basic quantities, like what is angular displacement. Angular displacement is nothing else, just the angle you can take by moving from the zero position to here. Do you hear the mouse on the screen in the YouTube? Can you validate? Do you see the how the mouse moves on the YouTube? All right. So here you can see this is the theta equals 0. This is technically the origin, and this problem is right now one-dimensional problem because we move only on the line of the circle. So angular displacement is nothing else, just let's say we moved from the zero position 60 degree. The only trick is we do not use the degree, instead of it we use the radian, not the radius, the radial, the rad. Its unit is the pi. Pi is the half circle, so the 180 degree. So pi over 2 is 90, for example, 3 pi over 2 is 270, and so on. Let's suppose we can determine the angular displacement, how it depends on time. It's like a one-dimensional motion, how you move, like, for example, at t equals 0, I'm at 0, at t equals 1, I'm pi over 2. Oh. All right, some of you doesn't hear me. Double check it. Now you can hear me. Can't see. Oh, lots of answer coming. Oh, all right. All right. Hmm. All right. Let's just set up some thing. Just a minute. No? Do you see the mouse? Oh, finally. All right. So, once again, angular displacement is nothing else, just we can say this is the origin, the theta equals 0. It's like in the x-axis, you have to say where is the origin, and then we move on the edge of the circle. That means we pass the unit 1, unit 2, 3, 4, or you can define any unit, but you have to say what is the unit. In this case, the unit is, for example, the pi. Pi is the angular displacement of 180 degree. And this is, so technically this is the angular displacement, how the theta changes by time. As in the x-axis, the xt was how we move on the x-axis, how the x changes on time, and the theta t is how the theta changes on time. Angular velocity is the omega. Omega is the derivation of angular displacement. So like velocity, or at least the x component of the velocity, we can get by derivating the xt. Omega you can get by derivating the theta. One other step, the beta, angular acceleration. It's not a big surprise. If you derive again, you can have the angular acceleration. So another two things, the period time, since if we want to move, for example, from this origin, the theta equals 0, if you move enough means 2 pi, you will come back in the same position. The period time, how long does it take to move from one position back to the same position? Of course, you can start your motion here also. So this is the period time. If you divide the 2 pi with omega, you will get a number in second. The frequency is the inverse of the period time. So technically, if you move like this, so for example, if it takes 2 seconds to move from the theta equals 0 to theta equals 0, if it's 2 seconds, 1 over 2 is 0.5, this is 0.5 hertz. Technically, the frequency is how many times you take one full circle in a second. Let's continue here. As in the test, I can give you instead of xt, a theta t. Theta t depends on time. If you derive it, you can have the omega. If you derive it again, you can have the beta, the angular acceleration. Small things. So for example, we can calculate the theta t equals 0. This is pi because these parts are 0. The only which is non-zero at t equals 0 is the pi. So at t equals 0, I'm here. At 1 second, pi over 2 times 1 square root pi over 2, pi over 2 times 1 is pi over 4 times 1 is pi over 4. That will be 3 pi over 2. So at t equal 1, I'm here. At t equal 5, if you write 5 instead of t everywhere, you can have like 17 pi over 2. It's not too easy to show directly where is the 17 pi over 2, so it's worth to divide this result into two parts. One part is this is the full circle. Technically, this is 2 pi. So it 4 times 2 pi means 4 times I go through the theta t equals 0, and then the rest is pi over 2, I'm here. So at t equals 0, I'm here at pi. At t equals 1, I'm here. But at t equals 5, I'm here. And at t equals 10, for example, it was 14 full circle plus pi over 2. So again, I'm there. This is how we calculate the angular velocity and angular acceleration from theta t, from angular displacement. But it should also work upside down. So if we know the angular acceleration and we know the so-called initial position in theta and in omega, so initial angular displacement and initial angular velocity, by integrating you can have this theta t. So this is absolutely the same story what we did in one-dimensional motion. So from xt we can calculate the vt at, and also from at, knowing the initial position and initial velocity, we can calculate the xt. The only trick is divide the result into n times 2 pi, into how many times I pass the theta t equals 0, and plus the residual to be able to show where is the body on the circle. Small things, even the angular velocity, and if you multiply the angular velocity with the r, you can have the speed of the body. Even for universal or universal, so constant angular velocity, the velocity vector changes since it moves around. And if this v, the absolute value of v is constant, so for example 1 meter per second, but here it points this direction, here it points that direction. So if you calculate the difference of the velocity, you will have some non-zero delta v. So once again, for constant circular motion, the v, the translational velocity vector, changes. There is delta v. If there is delta v, if we derive it with delta t, we can have acceleration. So for constant speed v, we need a so-called centripetal acceleration to keep this body on a circular path with the radius r with the v velocity. Its magnitude is v squared divided by r. If we have a ball, since there is acceleration, we can talk about force. It's simple acceleration, a centripetal force, which is nothing else, just multiplying m times ac, m times v squared over r. You can experience it if you try to rotate a ball with a string, and if you rotate fast enough, the string can break. That was the force that break the string. And if you look at the motion of the body, if there is no more forces, based on the Newton first law, if there is no force on the body, let's forget the gravitation now, the body will move with a constant velocity. Constant velocity means it will move in a tangential path. It will move like a free body, so with a constant v vector. So constant speed and constant velocity doesn't mean the same. Here we have a constant speed, but not a constant velocity, and that will causes the acceleration. All right. We will come back to the energy, potential, and so on, but let's solve some example with this rotation. So what I said, the angular speed, angular velocity is the derivation of theta t. and it has a direction. If this body move like this on the picture, and this is a right hand rule, this finger will show the direction of the omega. And if you speed up the rotation of this body, if the omega changes, you can calculate, you can derive it with time, and you can calculate the angular acceleration. So sorry, for some case it seems to me I use alpha from some book. In the English books we usually use alpha for angular acceleration. In the Hungarian book I use beta, and sometimes it seems I mix it. But alpha, beta in this circular motion means always angular acceleration. All right. The velocity of this body, so the v, is nothing else just the omega cross r. Fortunately, we will use only examples when the r and the omega is perpendicular. You can see, so the r will point in a radial direction, and the omega, you remember, the omega point towards to you. So if you can imagine a vector from the screen towards to your head, that is the direction of the omega based on this one. So if you see, for example, if you see how my mouse moves, this circular motion has omega towards to you. And since the r is in the plane of the screen, the omega is perpendicular to the screen and towards to you and point to you. These are perpendicular, and fortunately we don't have to play with this cross product, which is not an easy mathematical calculation, but you can write r times omega. All right, so we can calculate the v. In this case, this is r times omega. We can calculate the centripetal acceleration, which is v square times r. And if you also has an angular acceleration, that will cause, I mean, a faster and faster omega, that will cause a so-called tangential acceleration. And this tangential acceleration is the derivation of the velocity. This is r times angular acceleration. So we have a centripetal acceleration that's omega square r, or v square over r. That comes from the fact that the body moves on the circular path. And if you speed up this rotation, that will cause angular acceleration, and multiplying with r, that will gives you the tangential acceleration. So as sum of these two vectors, we can talk about the global acceleration of the body. That's the kinetics of the rotation. For the rotational energy, it's not that easy to calculate, since the formula of the kinetic energy is 1 over 2 mv square. But look at it. So here we have a small fraction of the body, and you can calculate the m times v square pretty easy. But if you move closer to the axis of the rotation, the v will be smaller, since the v is the r times omega. And even the omega is a constant, since we change the r, the v will be different. So for every, or almost every, small cubes of the body, so if you divide the body that rotates into small cubes, it can be very, very small, so infinitesimal small cubes. The mass is okay, so if the density of the body is a constant, the mass is nothing else, just the density times the volume of this small cube. That's unique for all the small cubes in the body. But the v depends on r. So here, well, for example, 1 cubic millimeter or 1 gram body will have 1 over 2 mv square, so small kinetic energy, and here where the v is pretty large, since v equal r times omega, and if the omega is constant, increasing the r will increase the v. You can't calculate easily the kinetic energy of the body. If we play with this formula, so instead of vi, we write omega times ri and use the square, you can have a formula which is similar to kinetic energy. So instead of 1 over 2 mv square, we can say 1 over 2 miri square times omega square. And if you want to calculate the full kinetic energy of the body, you can sum over all these small volume, and this sum, so sum over all the small volume of the body, this will gives you the moment of inertia. The moment of inertia, if you also want to calculate the moment of inertia for example, for inhomogeneous bodies where the density can change position to position, that's not easy. That's a volume integral, which is a three-dimensional integral. It's not the easiest way we can calculate, but for simple homogeneous object, I mean the raw densities is the same everywhere, we can have formula. For example, for cylinder, it's 1 over 2 mr square. So this is the radius of the cylinder, the mass of the cylinder, and you can see in the formula, so if you rotate the cylinder along this axis, you do not even have to worry about the length of the cylinder, since it does not depend on it. If you rotate let's say a full ball or full solid or a full sphere, it's 2 over 5 mr square. If this is like a basketball ball, it's 2 over 3 mr square. So today we will learn how to calculate rotational kinetic energy for a different body. This is a cylinder. The radius is 0.2, the mass is 10 kilogram, the omega, the constant angular velocity is 10 1 over s, and the length is 1 meter, but we know and we will see that the length doesn't matter. The rotation kinetic energy is 1 over 2 moment of inertia times omega square. The moment of inertia for a cylinder is 1 over 2 mr square. So let's calculate the rotational kinetic energy. 1 over 2 momentum of inertia times angular velocity square. Let's write here this 1 over 2 mr square, and if you calculate it, at the end you will have, this is 10 joule. And look, so if you rotate along this axis, it can be 1 centimeter or 1 meter long, doesn't matter. Of course, if you rotate this cylinder with the horizontal axis, the L should be in the formula. Alright, let's rotate the ball. For example, in this case, a full sphere, same dimensions, 0.2, radius 10 kilogram, and angular velocity is 10 1 over s. If we calculate it, this is 8 joule. So, by the way, have you managed to join to the Moodle course? Let me check it. This is Basics of Physics Moodle course. In the Neptune, I tried to send you an invitation to join to this e-learning course. This is the Moodle. Oops. Wait a bit, I can increase the letter, I hope. Yes, but only these ones. Let me see the participants. Enrolled user. Oh, nobody. I missed something. Wait a bit. Enrollment methods. All right. Can you double check your Can you write the course of the Neptune code of this Basics of Physics? Because I've chosen this one and perhaps it's not yours. Basics of Physics. This is for informatics student. What's that? So let me check your Neptune course code. Just a minute. Because technically I can invite you to this course. So you are the Basics of Physics, TTFBE 2101. TTFBE 21. Oh, I can't find you. Yes. This is the Basics of Physics. I've chosen your course, TTFBE 2101. All right, now let's save it. Have you received, and can you change it? Do you receive any Neptune message? If not, do not worry. Can you go to the Moodle? Oh, I have to log out. If you go to the Moodle, please choose. Oh, let me know when you are there. So just log into the Moodle. Choose this MISC English courses. And choose the basics of physics. And from here, I don't know what you will see. Oh. Are you here now? All right, go back. So this is the Moodle. You can find here the English courses for any other, so Miss Calliers or I forget the pronunciation of this one. The mixed English courses, and the first one is your course. All right. So this is the first page. All right, let's choose the English. This is the opening page of the Moodle course. Let me know when you are here. And try to find this one. Are you here? Can I go further? Write something in Discord. Are you here? Are you in this Moodle phys unidep.hu? First step, next step, final step. You can start with the third one also. Are you there? And the code for enrollment is ESB. Well, answering that question, sorry. So for us, this is the so-called normal e-learning system, this Moodle. I don't know the others. All right. Have you registered for the course? So this is the ESB, Earth Science Biology. This is the enrollment key. Let me see. Oh, I have to log in again. Technically, when you choose this self-enrollment, it will ask for a key. And the key is this ESB. But since I'm a teacher, no, I don't know how to go further. But perhaps there are. Oh, I can see you. Great. It's even better. All right. So now, how will we do this course? This is today. And for example, I can give you the lecture. Just a minute. Now, if you are in the course, do you see the lecture link? So for example, solve the examples in the page. Let me see where we were. 127. 127. Create a doc how you solved and upload. Oh, there are so many things. So if you click on the homework and you solve it, here instead of these buttons, you will see like upload or something. You can upload it and I will see it at your name. Can you try to do that from the list of dates? How do we find the enrollment options? Where is the lecture link? Oh, the others. Can you have the one? So I mean the lecture link is what I've sent to you. Oh, that link. Oh, sorry. That should be. I mean just here. Just click on it and you can see the same lecture. Or we can try to upload the lecture itself as a file. For example, add lecture as file and wait. Oh. Oops. Sorry. It takes time, but please double check. Oops. Is it here? I can't see. Drop files here to upload. Oh, it's here. Do you see the file? Alright, so from now we will communicate on this Moodle system, this e-learning system. I will upload the lecture, some homework, and if we can't write the test too, based on these homeworks, I can give you another grade if it's needed, or the ones they still need to write the test one can do here something. So of course I won't be able to check whether it's you or your physicist friend solve this example, so I have to find out something, but this is the platform we will go further. And if we can meet in the exam season, you can do some normal exam. If not, there are some exam options on this e-learning system, but I do not really trust this e-learning for exams, so perhaps we'll have an exam like Skype or something when I can see your face that it's really you talking about some simple physics. So, thanks for your patience. So solve it for cylinder full and empty balls, and then we can go further. Any other questions? Yep. All right, by the way, I stopped the